everybody. Thank you for joining Synthetic Intelligence Forum online. My name is Vic, and I'm very happy to have you here joining us today for a very interesting talk by Professor John Watrous from the Sheraton School at the University of Waterloo, and he's also the interim director of the Institute for Quantum Computing. And Professor Watrous has a very a provocative title for our talk, which is, will there be applications of quantum computing to data science? So without further ado, John, thank you so much for joining us in the Synthetic Intelligence Forum, and the floor is yours. Thank you.
Great, thanks, Vic. I appreciate the invitation to speak in this forum. The title of my talk, as you mentioned, is Will There Be Applications of Quantum Computing to Data Science? I'm sure it won't ruin the suspense for me to say that the answer to this question is that we don't know yet. And my aim in this talk is to offer my viewpoint and my speculations on this question. In terms of my own background and expertise, I've been working in the field of quantum information for about 27 years, since 1994. And I've been teaching students about quantum computing for over 20 years. So I understand how quantum computing works. I myself have not worked specifically on applications of quantum computing to data science. My expertise is in the mathematics of quantum information, including quantum algorithms and complexity, and quantum information theory. So that's the perspective that I can offer on this question. So here's a short outline of the talk. I'll begin by talking a bit about quantum information and how quantum information relates to quantum computing and to the notion of quantum advantage, or alternatively, quantum supremacy. To properly consider the potential applications of quantum computing to data science, I think it's important to start from that foundation. In the second part of the talk, I'll speak about a couple of specific approaches to applying quantum computing to data science, and particularly to machine learning. And I'll conclude with a few brief remarks on the future outlook of quantum computing and the possible applications to data science. The first thing I would like to do is to explain how quantum information is represented mathematically, which will allow for a more precise discussion of quantum computing and where the challenge in building quantum computers lies. If you don't understand all the details of what I'm going to be saying, it's okay. I'll try to keep it intuitive and simple. And it isn't necessary to have any sort of mastery over this material to understand the talk. There are actually two common ways that people describe quantum information. One is the so-called pure state description, which is a somewhat simplified description that people often learn first. And in the other description, which is the one that I will describe, quantum states are represented by a special type of matrices called density matrices. The density matrix description is more advanced. But I think it's actually, it leads to a more intuitive description of quantum information where quantum and classical information aren't really separate. Instead, ordinary classical information arises as a special case of quantum information, and it offers a way to model the effects of noise and uncertainty, for example. The density matrix description is something that anyone that works in the area of quantum information really needs to know about, because it's very useful and very powerful. To explain how this description works, let's start with what I assume is a familiar description of classical information through probability vectors. The idea is that if you have an ordinary finite classical system of some sort, such as a single bit that can be set to 0 or 1, then we can represent our knowledge of that system by listing the probabilities associated with the different settings in the shape of a column vector. For example, if we have a single bit, and we know for sure that this bit is set to 0, then we can represent our knowledge of this bit by the vector that you see here. There's a 1 in the first entry because this corresponds to the first setting, which is 0, because we're assuming that the probability for the bit to be 0 is 1. And the second entry is 0 because that entry corresponds to the second setting, 1, and the probability for this setting is 0. Another very simple example is a perfect uniform random bit, which is represented by this vector that you see here. We have a probability of 1/2 to be in each of the two states. In contrast, quantum states of finite systems are represented by matrices called density matrices, as I mentioned. And here's an example of a density matrix representing the state of a single qubit. I will explain what these different numbers mean in the next slide, but in case you're interested in precisely what the definition of a density matrix is, it's a positive semi-definite matrix whose diagonal entries sum up to 1. And if you happen to be interested in how this density matrix description relates to the more common simplified pure state description of quantum information, where quantum states are represented by vectors, the answer is that the state represented by a vector in the simplified picture is represented by a density matrix by taking the so-called outer product of that vector with its conjugate transpose. So we effectively multiply a column vector to a row vector to obtain a rank 1 square matrix. But it isn't really necessary to focus on this point right now. I'm just mentioning it for those that may wonder. So what do density matrices mean, and how do we interpret these different numbers that appear in these matrices? Well, we can think about density matrices at an intuitive level as follows. And here's a hypothetical example of a density matrix that we can refer to as we're discussing them. There's absolutely nothing special about this particular example. It's just an example. In this example, our density matrix is 3 by 3, and that means there are 3 distinct classical settings associated with the system that we're representing. The first thing to notice is that the diagonal entries of the matrix, meaning the ones along the main diagonal from the upper left to the lower right, form a probability vector. This will always be the case, given the definition of density matrices. You can think of this probability vector as describing the distribution of settings that you would observe if you were to look at the system when it's in this state. For example, if you had a quantum system in the state represented by our example density matrix, and you decided to open it up and look at it, you would see the first entry with probability 1/2, the second and third settings with probability 1/4. And in fact, ordinary classical states where there's nothing quantum at all going on are represented by diagonal density matrices, meaning that all of the entries off of the main diagonal are 0. Here's an example of a classical state. The diagonal entries happen to be the same as in the example density matrix on top, but now all of the off-diagonal entries are 0. Basically, we're representing ordinary classical information as a special case of quantum information. Given some probability vector that describes our knowledge of a classical system, we just put that probability vector on the diagonal of a matrix as we have here, with all other entries being 0. So the obvious question at this point is, what do these off-diagonal entries mean? And the answer is that these entries represent something quantum. These entries are 0 for classical states, and when they're non-zero, something non-classical or quantum is going on. Intuitively, they represent a superposition effect. For instance, in the first example, we can see the number 0.3 times I in this first row and second column here. And this number tells us to what extent the system is in a superposition between the first and the second settings. These are complex numbers, and we can interpret these numbers as consisting of a magnitude, which represents a strength of the superposition to some extent, together with a phase or an angle. That's the way we can think about a complex number. This may seem a little bit mysterious, and it's difficult to attach a physical meaning to these numbers because our everyday experiences are classical. But nevertheless, these entries are meaningful, and they have a very strong influence on the effects that various processes can have on these systems. Just like we have for classical information, processes performed on quantum systems are represented by linear maps. And if you want to know what a particular process does to a quantum system, say you perform some quantum gate, you can calculate this by doing some basic linear algebra on the entries of these matrices. And sometimes the outcomes will be very different when these non-zero off-diagonal entries are there. They'll get summed up in different linear combinations, and these phases or these angles will create the effect of interference. It could be constructive interference or it could be destructive interference. It just depends upon how all these different phases relate to one another. And finally, let me mention that the process that's known as decoherence refers to the tendency of these off-diagonal entries to shrink over time. This is perhaps a simplified picture of what happens in actual physical systems, but it does provide a useful way to think about the difficulty, or at least one of the difficulties, of building quantum devices. Nature has this tendency to constantly measure, or to do things that have the same effect of measuring. And this is why quantum devices generally need to be strongly isolated from the environment or the rest of the world to prevent or to limit this process of decoherence. This process is constantly causing quantum systems to become classical or to become more classical. And it can very quickly ruin any advantages that quantum information brings over classical information. So the picture that emerges from this density matrix description of quantum information is that quantum information is an extension of classical information. Even for one single bit, quantum information allows for more possibilities than classical information, both in terms of the states that the systems can be in, as well as the operations that can be performed on them. Through the study of this formalism of quantum information, we identify really interesting phenomena such as entanglement, non-locality, and quantum contextuality, which you may have heard of. And these things can all be experimentally verified in laboratories. And so what has happened over the last few decades is that a really rich interdisciplinary study of quantum information involving mathematics, computer science, physics, chemistry, engineering has developed, and it's a field with many interconnections among its different branches, as well as extra connections, if that's a word, to other areas of mathematics, science, and engineering. And there are many interesting potential applications that have been identified. And in some cases, these applications are already being put to use. A few broad categories include quantum sensing, where the aim is to build instruments based on quantum information that outperform classical sensors. Quantum simulation, which is exactly what it sounds like, where a system based on quantum information is built to simulate or to replicate a system of interest. Quantum information has applications to communication and cryptography, as I believe is very well known. And finally, quantum materials, where quantum information sheds light on the properties and the construction of different sorts of interesting and useful materials. We have teams of people working on all of these applications and others at the Institute for Quantum Computing at the University of Waterloo, for example. So quantum information has the potential for uses across a broad spectrum of application areas, but what about computation specifically? It's a very natural question, at least in retrospect, to ask if quantum information offers advantages in the context of computation. In other words, can quantum computation offer advantages over classical computation? Of course, this was a profoundly insightful question at the time it was first asked by Richard Feynman, Yuri Manin, and others, but it's also quite natural given the benefit of hindsight. Anyway, there's been quite a lot of work on this question beginning in the 1980s and continuing to today. And in theory, we have some pretty good reasons to think that quantum computing will offer significant computational advantages over classical computing. Surely the greatest discovery in quantum algorithms, at least in my view, is Peter Shor's 1994 discovery of efficient algorithms for factoring and computing discrete logarithms on a quantum computer. These are problems that are not known to be efficiently solvable on a classical computer. And as is well known, the difficulty of these problems is the basis for the security of widely deployed public key crypto systems like RSA, for example. The methods that Shor pioneered as part of this discovery have been generalized, and as a result, there are several additional computational problems that can be solved using these techniques, although none are quite so easy to explain as factoring, I guess. But these are generally problems with a very special algebraic structure that allows for what we suspect is an exponential advantage of quantum over classical computation. I mentioned simulation previously, and there has been a lot of great work on developing very sophisticated methods through which quantum computers will be able to simulate quantum mechanical systems of various sorts. This was the original motivation behind Feynman's idea to consider quantum computing in the first place. Quadratic speedups for quantum computing, such as those from Grover's algorithm and its generalizations, are also known. And more generally, polynomial speedups for other problems may be possible. These sorts of speedups could one day offer huge advantages, potentially in data science. In comparison, for instance, fast sorting and the fast Fourier transform offer slightly less than a quadratic speedup for the tasks they perform over naive or straightforward algorithms. And there's a very good argument to be made that these are among the most important algorithms that have ever been discovered. But quantum computing will likely need to advance considerably before quadratic speedups over classical computing become worthwhile. There are a variety of more theoretical, restricted settings where quantum computing offers advantages over classical computing, such as in query complexity and communication complexity. It's probably best to think about these settings as being more like sandboxes where methods can be developed that may or may not have practical applications. And finally, there has been a lot of work on general frameworks and methods, including ones that unify some of the ideas behind the algorithms I've mentioned. And some of the ideas here are really quite beautiful and provide us with tools that are in some sense ready to be brought to bear to problems that we might not yet have considered. Quantum walks and the recent quantum singular value transformation method of Gillian, Su, Low, and Wiebe are examples of quantum algorithmic frameworks that have been studied. There are also many computational problems of interest, including ones with great practical importance for which we don't think that quantum computing will help all that much. For example, it's generally believed, although we don't have a mathematical proof to support that claim, that NP-complete problems are too hard for quantum computers. Intuitively speaking, there just isn't enough structure there to allow a quantum computer to build up the sorts of delicate interference patterns that allow for an efficient algorithm for factoring, for instance, at least as far as we know, or as far as we suspect. Just as an aside, I should mention that quantum computing could lead to better approximation algorithms for NP-complete problems, where we aren't necessarily looking for the optimal solution, but just a pretty good one. But we don't actually have any good examples yet where this is known to happen. And finally, let me mention that there is a lot of potential for heuristic quantum computing methods. And I'll mention this again in the context of data science and machine learning in particular. But we just don't really know yet. These are things we're going to have to test and experiment with as quantum computers continue to develop. I'm sure I don't need to say it, but I will anyway. It's very difficult to build a quantum computer. To do it, one needs to isolate the computer from the rest of the world to limit this process of decoherence. But simultaneously, the user or the programmer needs to have very, very precise control in order to perform the necessary operations to make the algorithms work. And that includes the ability to initialize the computer and to read out the answer at the end of the computation. And somehow squaring these two demands is really quite a challenge. There has been some really remarkable progress in doing this over the last several years, but we're still quite far from building large-scale quantum computers. To put things in perspective, we can reasonably expect that quantum computers will need to increase in both size and coherence time by several orders of magnitude before we can factor a number using Shor's algorithm that we can't easily factor classically. Before I get on to the second part of the talk on applications of quantum computing to data science specifically, I'd like to make a few comments about the nature of quantum advantage, or alternatively, quantum supremacy. People have slightly different preferences for the terminology they use, And they mean slightly different things when they use these different terms. But for the sake of this discussion, let me suggest the following interpretation of what quantum advantage means. Quantum advantage refers to the situation in which quantum computing has allowed for something to be computed more efficiently than would be possible using classical computing alone. And here that situation is expressed informally as an inequality, where quantum computing plus classical computing is greater than greater than classical computing alone in some respect. What we're talking about, in essence, is the situation in which quantum computing helps to accomplish something, and it need not be a particularly useful task, although, of course, we would hope that that would be possible. And now the question is, how does one actually demonstrate a quantum advantage? And my answer to that question is you really can't, and you probably shouldn't claim it. The best you can realistically hope for is to use a quantum computer or a quantum-assisted computation to accomplish a task in a way that's better than what is known to be possible with classical computing alone. And what's particularly important here is that we really need to let classical computing respond. It's not a convincing demonstration of a quantum advantage if nobody ever bothered to solve the problem classically. That means letting classical algorithm designers, computer architects, and others have a chance to accomplish the same task classically. And it's only when classical computing fails to respond that we should really start to gain any confidence that quantum advantage has actually been achieved. Obviously, if you have a particular task you want to solve and the best method available is a quantum method, then you should use it. But what I'm trying to do here is to explain the nature of quantum advantage and the difficulty of demonstrating it. You will sometimes read or hear about alleged quantum advantages, but you have to be wary. And in particular, I think you have to consider how much focus and determination was actually put into the classical computations to which these comparisons are being made. And we saw this in 2019 when Google claimed quantum supremacy. And almost immediately, IBM questioned their estimates for how long it would take to perform the same task classically. And there are some very recent claims that you can actually replicate these results that were obtained by Google using not all that many GPUs. Keeping in mind that you could probably purchase many thousand GPUs for the cost of a Google Sycamore processor, coupled with the fact that classical algorithmic advances can perhaps be brought to bear on the problem that Google solved, which is a random quantum circuit simulation problem that classical computer scientists really haven't tried all that hard to solve or thought all that much about. And so I think it's reasonable to say that the jury is actually still out on quantum supremacy. But I would like to stress that this is actually a really useful and productive dynamic that plays out in a variety of different settings. It's like a competition or a game in a way, and it can lead to advances on both sides. I'll mention this same general sort of dynamic a bit later, which led to classical advances in machine learning, at least in a theoretical arena. So the bottom line is that one should be cautious in interpreting claims of quantum advantage or quantum supremacy. And now I'll move on to the second part of the talk, which is about quantum computing for data science and machine learning in particular. So it's often claimed that quantum computing will have applications to data science and especially machine learning. And in fact, it's fair to say that quite a lot of hope has been pinned on quantum machine learning. In terms of concrete proposals and approaches, I will discuss two main families of approaches. The first is quantum machine learning on a quantum computer through quantum linear algebra on state encodings of data. And the second is the idea of learning quantum circuits, or alternatively training quantum circuits to do interesting things, which includes ideas such as quantum neural nets. This category connects with the notion of a variational quantum algorithm. And this is a very active area of research in its own right, independent of data science applications. I don't claim that every idea for how quantum computing could be applied to data science falls into one of these two categories, but in my assessment, these are the two main categories of approaches that have been proposed. Before moving on to these two categories of proposals, however, let me mention a critically important issue that in my mind needs to be clarified right from the start whenever quantum computation for data science in general is under discussion. And that is, how is the data actually given to the quantum computer? This issue is often not adequately addressed, let us say. If a quantum computer is capable of very quickly solving a particular problem once the data is already loaded somehow into its memory, but for some reason it takes a very long time to prepare the memory prior to the computation, then there may be no advantage. So we have to keep this in mind. And in particular, we have to keep in mind that most likely for quite a while, quantum computers are going to be much, much smaller than classical computers with respect to data storage or information storage. And when we're talking about data sets that are of a size that's relevant to data science, we have a very, very serious issue on our hands. So let's begin with the first category, which is quantum machine learning based on quantum linear algebra on state encodings of data. And the idea here is motivated by a 2009 algorithm due to Harrow, Hassidim, and Lloyd, which is colloquially known as the HHL algorithm, which performs a task that I will describe shortly. And this is a quantum task. What I mean by that is this is an algorithm where both the input and the output are quantum states. So you would probably expect this algorithm to be used somehow as a subroutine inside of some larger quantum computation. And the way it works is as follows. So let's imagine we have n qubits for some positive integer n. So n represents the size of our quantum computation that we're performing. Let's take capital D to be equal to 2 to the power n, which is the dimension of the space that we use to represent quantum states of our n qubits, either as d by d density matrices or d-dimensional unit vectors in the simplified picture. And notice in particular that d is in general much, much larger than n. It's exponential in n. Let's also suppose that v is a d-dimensional unit vector, which should be thought of as a pure state of our n qubits, and let's let m be a d by d matrix. So what the algorithm does under pretty strong conditions on the matrix M and on the way its entries can be accessed by a quantum computer is to transform rather the quantum state corresponding to the vector v into a new quantum state that's either equal to or proportional to m inverse times v. And it does this in time that's polynomial in n. Here, I'm trying to keep things simple. I'm not going to explain the conditions on m or how good the approximation is, but these things can all be made precise. And by the way, if this seems a bit technical, it's okay. I'm just trying to explain the basis for these proposals. And it isn't necessary to understand the technical details, really. Anyway, why is this interesting? Well, it's interesting because M is a very large matrix. It's exponentially large in N. It would take time exponential in N rather than polynomial in N to invert this matrix classically. And in fact, it would take exponential time just to write it down. But here the computation takes just polynomial time in N. So there's a sense in which we're getting an exponential speed up by using this algorithm. But it must be recognized that this is, it's in some sense comparing apples with oranges. The input and the output here are quantum states, so a direct comparison with classical algorithms isn't entirely meaningful. But it is really interesting that this can be done. And we now recognize this as just one linear algebra related task among many that can be performed efficiently by a quantum computer. For instance, rather than inverting a matrix like this, we could choose to perform a matrix exponential. And that's closely connected with the problem of simulating the evolution of a quantum system according to the Schrodinger equation. So what this has to do with machine learning is that many algorithms and methods in machine learning are based on linear algebra. And so we might hope to leverage this methodology in the service of machine learning and possibly get an exponential speed up through quantum computing. That is, this exponentially large value of d that I referred to on the last slide could be proportional to the amount of data we're working with. And this could potentially lead to a very significant quantum speed up. For example, in 2017, Karanidis and Prakash proposed a quantum recommendation system based on these methods. And in this particular example, we have a collection of products that are either preferred or not preferred by a collection of customers. And the goal is to provide recommendations to customers for products they're likely to prefer based on some reasonable assumptions about people's preferences. This recommendation system was, again, under certain assumptions about the way that it might be used, exponentially faster than the best known classical methods at the time. And it was particularly noteworthy because the authors put quite a lot of thought and effort into the issue of how you prepare the quantum state representation of the input data. Specifically, they developed a quantum data structure through which this task could be performed. You still need to build and populate that data structure, but they address the issue rather than effectively assuming away the problem, which is, as I suggested before, a noteworthy accomplishment. Several other quantum machine learning algorithms based on the same sorts of ideas were also proposed both before and after the recommendation system of Karanidis and Prakash, including ones for tasks that I've listed here on the slide. So the existence of these various approaches and the idea that they might provide an exponential quantum speedup caused quite a lot of excitement about applications of quantum computing to machine learning. But as it turns out, there are a couple of major obstacles to realizing such an advantage. I've already touched on the first obstacle, which is that these methods generally require quantum random access to large amounts of data. And that suggests that a large quantum device of some sort, or perhaps a costly procedure to get the data encoded into a quantum state, would be needed to use these methods. There have been various suggestions about how this might be done through the use of a so-called QRAM, for instance. But there's now a general consensus that this would likely be a prohibitively expensive thing to do. If we have to build a large quantum storage device and somehow get the data into it, we have to take that cost into account as we're comparing with classical algorithms. And it seems like this is going to wash away any advantages that would come from quantum linear algebra on data encoded into quantum states. There could be ways around this, such as quantum machine learning based on data that comes from a computation, and that computation could perhaps be performed in superposition directly by a quantum computer. Or it could be based on a way of pre-processing the data classically into a more representative form. But this seems like it might very strongly limit the applicability of these methods. The second obstacle is that very recent work, which was initiated by Yu and Tang in 2019, has revealed that we don't actually need a quantum computer to unlock the sorts of advantages that these methods suggest. What Ewan did was to say, fine, let's assume that a quantum computer can access data in a way that these methods require. But let's compare this to a classical method or classical methods that have an analogous but classical level of access to the data. And what she found was initially that the quantum recommendation system of Karanidis and Prakash can be simulated classically with just a polynomial slowdown. And that means that there will not be an exponential speedup coming from quantum computing for this particular approach. These methods have been generalized quite extensively, and we now know that quantum computing will not provide an exponential speedup for any of the machine learning tasks I listed on the previous slide through the quantum linear algebra approach. And this is an example of this dynamic that I mentioned earlier, where you have to consider the possibility that classical algorithmic advances will effectively rain on the quantum computing parade. And I would contend that this is actually very healthy. These methods were developed directly in response to quantum techniques. They were very much motivated by them. If you sell quantum computers, you probably don't like this, but science has surely advanced through this interplay. Now, there still could be a significant polynomial speed up through this approach, but for a complexity theorist like me, these dequantization results strongly suggest that we might look elsewhere to find quantum advantages. And based on these two obstacles together, my personal feeling is that quantum machine learning based on quantum linear algebra would seem, as it turns out, to have rather limited potential. I should say that quantum linear algebra itself still has great potential for simulation, for instance. And there is a technical sense in which any advantage from quantum computing can be unlocked through quantum linear algebra. But machine learning, through the sort of approach I've suggested here, holds less potential, to my eye. The second general family of proposals that I want to mention to leverage the power of quantum computing for machine learning involves effectively learning a quantum circuit, or to be more precise, learning how to best set a collection of parameters that control a quantum circuit. We refer to quantum algorithms that follow this approach as variational quantum algorithms or variational quantum circuits. The idea is that we have a particular quantum circuit or a quantum algorithm of a particular form with, let's say, some or all of the gates in the circuit controlled in some way by a collection of real number parameters along the lines that I've suggested here on the slide. This particular circuit I've drawn is not significant at all. It's just an illustration that's meant to convey the basic idea. It could be that certain parameters control single gates or multiple gates, and depending on the actual problem that one's trying to solve, there might be some significance to the layout of the circuit. And maybe this comes from an intuition about the problem or some knowledge about the particular problem that's being solved. By running the circuit and then measuring the output, we can compute or approximate some cost function. Or perhaps we can instead compute the gradient of some cost function. And we imagine that the goal is to minimize this cost function. It could be that it's enough to simply know the minimum, or maybe once we know a particular setting of the parameters that achieves some target for the minimum cost, we might then use the output of the quantum circuit to solve whatever problem we're trying to solve. So the evaluation of the cost function is performed by a quantum circuit or a quantum algorithm. But the techniques used to search for a setting of the parameters that minimizes the cost is generally assumed to be classical. And here we could use any technique we choose, including approaches based on machine learning. It could also be that there are additional inputs that I haven't pictured here on the slide that serve as training sets, for example. So in short, we can use quantum computation within machine learning or as an essential part of the machine learning approach to learn a quantum circuit or to train a quantum circuit to do something interesting. There's been quite a lot of work on this approach, and it's a very, very active area of research, and many specific application domains have been identified, including finding ground states of quantum systems, quantum simulation once again, various optimization and classification problems, and also compilation, meaning that we might have a particular action in mind that we'd like a quantum circuit to perform. Maybe it's something useful within a larger quantum computation. And we're effectively searching for a way to do it, to implement that operation efficiently. It's a very general and a very flexible approach. It's particularly appealing for so-called NISQ or noisy intermediate scale quantum devices because there's not a lot of overhead involved. An interesting class of examples that I mentioned before is quantum neural nets. And you can think of a neural net as operating in sort of a similar way. And by extending the way that a neural net operates to allow for quantum operations, or maybe just small parts of them will be quantum, possibly their power or their expressibility can be increased. There are a couple of caveats to this approach. First, this is a primarily heuristic approach, and it may be very difficult to predict how well it will work until we can actually try it in different settings. And second, we can reasonably expect that quantum computers will need to get a lot larger and perhaps less noisy before any evidence for a practical quantum advantage emerges from this approach. Nevertheless, I find this to be a really exciting direction. I'm strongly supportive of further research in this direction. I'm supportive of research in all of these directions. And now I will finish the talk with a few concluding remarks. There are certainly very high expectations on quantum computing, and there's no denying that there is some hype. However, it is a really interesting and exciting time for the field. We're just beginning to have access to quantum devices, and this is an important step that could signal an inflection point for the field. Through continued research, guided for the very first time by hands-on experience, we will surely improve and continue to improve quantum devices. And we will most likely discover new applications of quantum computing that we might not have even considered yet. At the same time, we have to keep in mind that large-scale quantum computing, as we envision it, is an enormous technological challenge. It's not going to be easy at all. We've made a lot of progress, and thus far we have not encountered fundamental barriers that would suggest that quantum computing is for some reason not achievable, but it's going to take a while before we get there, likely many years. And I think it's healthy to consider what it is that we're effectively up against. I spoke about the nature of quantum advantage, and I framed it as a competition of sorts between quantum computing plus classical computing against classical computing alone. And I think we have to respect classical computing. The development of the classical electronic digital computer represents one of the greatest technological achievements of our species, and we've been refining and perfecting this incredible technology for many years. And finally, because I think it is a really important point, let me reiterate that quantum computing is just one application of quantum information, which already has applications and can be reasonably expected to produce many more. And now for the very last slide, let me give you a more direct speculative answer to the question asked in the title of the talk, will there be applications of quantum computing to data science? It is certainly possible that a quantum advantage will be obtained, although we might only suspect it, for a task that is relevant to data science. This issue of how data is input into a quantum computer is just critically important, though. And to my eye, this seems like such a limiting factor that my tendency personally is to look elsewhere for quantum advantages, like quantum simulation, for example. The proposals to use quantum linear algebra to speed up quantum machine learning seem to have limited potential, both due to strong assumptions on data input and especially the dequantization results that I spoke about. On the other hand, I really like the variational quantum circuit approach. I suppose I've implicitly suggested this as an application of quantum computing to data science, and it could be. But really, I see it as a more general method that can incorporate techniques from data science. But one would hope that this method would have applications to a broad spectrum of problems and not necessarily to data science specifically. It's going to require progress on building quantum devices, and there will need to be more experimentation and certainly more theory before the potential of this approach comes into focus. When I hear some of the things that people essentially promise about quantum computing, how it will revolutionize machine learning, for instance, I feel concerned, to be honest. To me, quantum computing is a noble pursuit. We're doing something that we've actually been doing for thousands of years, which is to try to better use nature to satisfy our information processing needs. But overpromising isn't going to help, particularly in the near term. Current day quantum computers can in fact perform useful computations, but so can classical computers. And obtaining a quantum advantage is a really big challenge. At the end of the day, I would not expect a quantum advantage for a data science application anytime soon, but we should always respect future technologies, which historically we have tended to underappreciate. And so perhaps one day we will witness a quantum advantage for a data science application. So thanks for your attention. That is the end of the talk.
Thank you very much, John, for a very interesting, thoughtful and thought-provoking talk. We have a couple of questions here. So in the interest of time, I'll get right to the questions. So there's a question from Gordon, which is basically asking, can you comment on what classical computing knowledge is essential going forward to ensure that quantum computing successfully matures? And couple that with also, John, a comment from with response to that, which was about the quadratic unconstrained binary optimization as one of those aspects of classical computing knowledge. So what's your thoughts on the two parts to this question?
So let me focus on the first one, because I think I would need to think a little bit more carefully about the second part. So my initial thought is that knowledge of classical computing is going to be essential for quantum computing. There's a sense in which the question presumes that they're different, and I don't see that as being the case. I like to see quantum computing as being a part of computing. That it's really another step. It offers potential. Any kind of classical technique that you can imagine, it could potentially be incorporated into a quantum approach to a problem. So I think it's really specific to the problem, but in general, I would just say that a knowledge of classical computing is essential, and understanding what we can do with classical computing. And it would be difficult for me to single out particular areas of knowledge. I think that understanding them together is really the way to move forward.
Okay, excellent. Another question, John, and this is a question I had as well, as you were outlining some of the computer that can do data science. Is there sort of some work that you're familiar with, or is there even some purpose behind perhaps purpose-built quantum computers for data science? So specifically to solve classification problems as different from clustering problems, as different from regression problems, or are those problems kind of common to any of these types of canonical tasks of machine learning?
So the possibility to have special purpose quantum devices is a fantastic approach, because right now we're very limited in terms of the size of these devices, and building special purpose devices is a great approach in terms of. Okay, so it's asking possibility to have quantum devices specific to. So the answer is yes, of course. You could certainly build special purpose devices, and there are special purpose devices that are built. For example, D-Wave doesn't build general purpose quantum computers; they build quantum annealers. It's a very specific approach. If you have a particular quantum algorithm in mind, like Shor's algorithm, you can't run it on a D-Wave quantum annealer. But nevertheless, with an annealer, you can solve particular problems. Using this approach. So absolutely. In terms of, evolving in terms of getting smaller and smaller, this is certainly inevitable. This will be just a part of the progression. In the early days of computing, of course, computers were enormous. And, now we carry around these devices here that are, have, something like 1 million times the computing power of the ENIAC. And we can reasonably expect that the same kind of thing will happen with quantum computers. It's just going to be part of the equation. People often point at Moore's law and the barrier that quantum theory presents to Moore's law. I mean, I think that is a really important point. And who knows, perhaps as we get closer and closer to that boundary, quantum devices will improve and get smaller and smaller, and the classical devices will improve and improve. And at some point, maybe there won't be very much difference between them. I mean, that's probably in the distant future, but that potential is absolutely there.
Thank you, John. And perhaps
when we think about, sorry, go ahead.
No, I was just keep going. Thank you.
All I was going to say is that when we think about what has happened in the last 75 years, I mentioned the ENIAC, which is a little more than 75 years old, the very first, or often considered to be the first electronic digital computer. It's truly astounding what has happened. And 75 years ago, if you had told somebody about what we have today, where you can talk to your watch and you'll actually get a meaningful response from your watch with global connectivity and so on, nobody would have believed this. So 75 years from now, who could possibly say what we will be able to do with quantum computing? I mean, this is part of this, respect for future technologies that I think we have to always keep in mind, that most likely we will be very, very pleasantly surprised by what happens.
Thank you, John. That's excellent. Maybe we can do two more quick questions. One question here is to summarize, I know you touched on this, John, but what are variational quantum circuits?
Oh, okay, so this refers to this idea where we have a quantum circuit, and each of the gates, or perhaps just a collection of the gates, are in some way controlled by a parameter, perhaps a real number parameter. And so you can effectively tune this as if you were almost thinking about a knob on each of these gates. And so as you tune these different parameters, different things will happen. So that is what a variational quantum circuit is. You're varying the parameters of the circuit, and as a result, it is doing different things.
And is the idea, John, that in a data science type application that you would have some kind of fitness function, such as you want to minimize loss, and so you want to have those knobs sort of in the configuration that minimizes that loss or something?
Absolutely. Like this is what I refer to as the cost function, but a loss function, you could interchange these words for the sake of what I've described. Absolutely.
Sure. Okay. So you could map any kind of objective function to it, and you can kind of have it go in that direction. Okay.
That's right. And it's a very, very general approach. There's many variations on what I suggested that you could consider. There could be continuous evolutions and so on.
Okay. Here's another question, John, which is, can we use classical machine learning to train a quantum circuit?
Yes, this is exactly this is one of the approaches to the variational quantum algorithm, the variational quantum circuit approach. You can imagine different techniques that you would use to try to optimize these parameters, and using classical machine learning to do this is one of those methods, possibly through training sets or any other approach really that you would use to classical machine learning.
Okay, and just one last one, John, is what is an example of naturally occurring, if there is any, of data that is in quantum form?
I'm trying to just digest this question a little bit. What is an example of naturally occurring data? Well, I keep on coming back to simulation, and I don't know if that would be a good example or not, but you could think of a quantum state itself as being data that somehow has arisen from some process that you'd like to manipulate in some way. I'm not sure that I would, it's really natural to think of that as data, but that's what comes to mind. I mean, when I think about data, I think about classical data. And so it is in some sense different, but I think you could probably imagine a situation where you had a quantum state that was produced by something. You wanted to know something about it. You wanted to change it in some way. And that's my answer to that question.
Okay, thank you. With that, John, that brings us to the conclusion of our talk. Thank you so much for sharing your insights and foresight about are there applications of data science, and we'd love to have you back in the future to maybe discuss further state-of-the-art advances. As you noted, there's a couple of developments you cited in your work, in your talk today from 2019, 2020. So I know this field is rapidly evolving and maturing. So we'd love to have you back, John, in a couple of months to hear about an updated landscape. But thank you so much, and we hope to have you back soon. Thank you.
Great, thank you.
Okay, bye for now.